Hello and welcome to lesson 5.7, the squeeze theorem. So today what we're going to do is we're going to look at what is called the squeeze theorem that helps us actually calculate a limit of a function, either an indefinite limit or a definite limit, based on a fact that we can look at it between two different functions. So for example, let's say we have two different functions, f of x and g of x. We're going to say g of x and h of x. So g of x, I'm going to draw as this kind of function right here. Looks like some sort of parabola. And let's say we have another function, h of x, which is another parabola, like this one. So that they basically touch in one specific spot. Let's call this value that they're getting close to each other, the value of c. So let's say we do have another function that actually is called f of x. It goes right between these two functions, right here, at the same spot. So the squeeze theorem states, if you can actually prove the limit as x approaches c for g of x equals the limit as x approaches c of h of x is equal to some value L, where this function g of x, f of x, and h of x are, f of x is between g of x and h of x for all x values not equal to c, or about that value c, then you can find that the limit as x approaches c for f of x is equal to L. So let's use this in this context right here. So first of all, notice that cosine of 2x is between the values of -1 and 1. Moreover, if that's the case, -1 over x squared is less than or equal to cosine of 2x divided by x squared, which is less than or equal to 1 over x squared. Now, we know that the limit as x approaches -infinity for -1 over x squared is equal to 0, which is also equal to the limit as x approaches -infinity for the function 1 over x squared. So therefore, what we can say is now, due to these two limits equaling 0 as x approaches -infinity, then the limit as x approaches -infinity for this function cosine 2x over x squared is also equal to 0 due to the squeeze theorem. Now, most of the time, we're going to be using cosines or sines to actually prove this function, because we do know that sine and cosine are in between values. But you can also use this in terms of in between an exponential function and a linear function, let's say, or two exponential functions. Okay? So let's take a look at this example right here. So first note that because this function is a squared function right here, it's not actually going to be negative. It's going to be between 0 and 1. Well, if we multiply x squared by both of these, so x squared times 0, x squared times the sine squared of 1 over x, and 1 times x squared. Well, that's just going to give us 0 is less than or equal to x squared times sine squared of 1 over x which is less than or equal to x squared. Well, the limit as x approaches 0 of 0 is equal to 0, which is also the limit as x approaches 0 of x squared. So that means, therefore, the limit as x approaches 0 of x squared times sine squared of 1 over x is also equal to 0, again by the Squeeze theorem. Okay, so let's move on. Now, due to the sum properties of some functions, it's not able to calculate the limits of some functions. So, for instance, sine of x, to approach it from the left and from the right to as the limit gets close to 0, it's not possible to actually know until we investigate some more properties later on. So that means you have to actually know what the function looks like. So this is the actual function f of x here. And based on the graph that you can see right here, even though the value doesn't actually exist right there, there's actually a hole right there, it's not being shown, the limit as x approaches 0 for this function is equal to 1. We're going to need to know this information for the next example. So, let's take a look at this one. Let's calculate the limit as x approaches 0 for the function tan x over x. Well, as we know, we can break up limits in terms of other ones. So tan x is sine x over cosine x, and this is multiplied by 1 over x. Well, we can rewrite this in terms of limit as x approaches 0 of sine x over x times 1 over cosine x. And again, what we can do is we can break up limits in terms of multiplication. So we can work out the limit as sine x over x. We can multiply it by the limit as x approaches 0 of 1 over cos x. Well, we just investigated the fact that limit as x approaches 0 of sine x over x is actually 1. And the limit as x approaches 0, we can actually substitute 0 in there. That's also 1. So this limit actually turns out to be the value 1. We can also use replacements of variables. So let me show you what I mean by that. So to calculate this limit as sine of 1 over x approaches, limit as x approaches infinity of sine of 1 over x. Well, notice as the limit as x approaches infinity of 1 over x is equal to 0, we know this value. Therefore, what you can also do is you can say as the limit as u approaches 0 here for sine of u, that also equals 0. So as you can see, as x approaches infinity, 1 over x approaches 0. So as x approaches infinity, so limit as x approaches infinity, sine of 1 over x also approaches 0. And this is actually a substitution of variables. Since we know 1 over x gets closer to 0, then we can replace that variable. And thus concludes the Squeeze theorem.